Myself Nancy from PSC Chemistry Honors first year making video on liquid state. Introduction in solid, the constituent particles are closely packed, hence they are possibly rigid and have a definite volume and a definite shape. In gaseous, the molecules are completely free to move about there and they have neither a defined shape or nor a defined volume. They fill up the vessel of the any volume and take place a shape that of volume vessel. However, in a liquid, the molecules are not fixed in a solid state, as in a solid state, and same time they are with freedom of motion that are not as of solids. Like the solid, they have a definite volume, whereas solid state, but the gaseous state do not have a definite shape. It takes place of the shape of the vessel in which they are put and expressed by saying that the liquid state is intermediate between the gaseous state and solid state, as explained above. And the difference in the behavior of three states of matter is mainly due to the intermolecular distance of separation. In solid state, the constituent particles are closely packed, almost touching each other, and may be treated as a hard as sphere. In a liquid, the molecules are separated by the smaller distance, while the gas intermolecular distance are so large that of the molecule can be moved randomly within the molecule, and the arrangement of the particle of the three state of the matter in the two-dimensional space may be represented as follow. The intermolecular distance between the cohesive force, intermolecular force of attraction in which in a solid is very strong, as in the case of gases. They are very weak, and in the case of the liquid, they are in between, and they are fairly strong to keep them constant state that, but not strong enough to vapor hold them to a fixed position. In fact, all the characteristic property of a liquid such as vapor pressure, surface tension, viscosity are due to the nature of intermolecular force existing in a liquid. Intermolecular force on van der Waals force. The force of attraction exists between the molecule of substrate are called intermolecular force or cohesive force. These forces of three different type are explained below. First is dipole-dipole interaction. The force of attraction occur among the polar molecule. The reason for this origin of these forces is quite observed. The polar molecule has been permanent dipole, and the positive pole of one molecule is thus attached by the negative pole of the other molecule. A simple example of the HCl, in which the chlorine has been more electronegative, acquire a slightly negative charge, whereas a hydrogen and become a slightly positive charge. The dipole-dipole attraction then take place among the HCl molecule as shown in figure 2.2. The proof for such existence of dipole-dipole force is, if the dipole-dipole force exists among the polar molecule, they should be have higher melting point and boiling point than the non-polar molecule, provide all the phases like molecular mass, molecular shape, etc. are the same. This is actually found to be so. The example for non-polar molecule NO2 has been boiling point of minus 196 degrees Celsius and minus 183 degrees Celsius respectively. So whereas the NO have a slightly polar as higher boiling point of minus 151 degrees Celsius. Magnitude of dipole-dipole moment forces, as the charge at the end of the polar molecule are not as so great as the charge on the ion molecule. In an ionic compound, the magnitude of dipole forces is therefore much smaller in comparison to the ion-ion attraction or ion-dipole attraction. Further, whereas the force of attraction between two ions is inversely proportional to 1 by r squared. The force of attraction between two dipoles is exactly proportional to 1 by r to power 7, where the r is the distance between the ions in the former and in the case, and that the dipole in the later case But under the similar condition, temperature and pressure, since the intermolecular distance are very large and dipole-dipole force of attraction among the gases and molecule are very small. As the pressure is increased and or the temperature is decreased, the distance among the molecule is decreased and the molecule come closer. As a result, the intermolecular force of attraction increase as the gas changes into the liquid or solid. The magnitude of the dipole force is different from the polar molecule can be predicated on the basis of the polarity of the molecule, which is turn depend upon the electronegativity of the atom present in the molecule and the geometry of the molecule. The polarity of the molecule are usually expressed in the term of dipole moment of the molecule. For example, the comparison of the molecule of NH3 and H2O dipole moment is 1.49 and 1.85 D respectively, and thus the both of these are nearly the same molecule mass and the intermolecular force of attraction are stronger in the case of H2O than the NH3, and constantly H2O has a higher melting point and boiling point than the NH3. In fact, it has been well known that whereas H2O is liquid and NH3 is gaseous, hydrogen bonding. It is a special case of dipole-dipole attraction. It occurs in the molecule containing a hydrogen atom linked by a covalent bond is to highly electronegativity atom, but small air is the size because of the large electronegativity difference between the hydrogen atom and the highly electronegativity atom. The hydrogen atom acquire a significant positive charge and the negativity acquired does significantly negative charge. The positive hydrogen and one of the molecule that the attractive of the nature. The electronegativity of the other molecule, for example, the case of HF, H2O, and NH3 may be represented as the following given below. Because of the greater polarity of these molecules, the intermolecular force of attraction are stronger than the ordinary dipole-dipole attraction, and that is why they are intermolecular attraction is considered as a bond rather than the more dipole-dipole attraction. This type of bond is called hydrogen bond and represented by a dotted line as given as shown in the example above. Hydrogen bond may be defined as attraction of hydrogen atom of one molecule by the electronegative atom of another molecule. In the case of compound, the containing hydrogen atom linked to the highly electronegative atom and smaller in size. Further, as shown above, in the cases the hydrogen atom is linked to the electronegative atom similarly, one by the covalent bond and another by the hydrogen bond, and these thus the hydrogen bond act as a bridge between the two electronegative atom, and this is sometimes referred as hydrogen bridge. Strength of the hydrogen bond. As the mentioned above, the hydrogen bond is stronger than the ordinary dipole-dipole attraction, and however it is weaker than the covalent bond, and the energy of the hydrogen bond lie between the 20 to 40 kilojoule, whereas the covalent bond is depend upon the 160 to 600 kilojoule per mole. Depending upon the electronegativity, the strength of hydrogen bond follow the order. Second is dipole induced dipole attraction. The positive end of the polar molecule may be attract the electron and cloud of the non-polar molecule lying closer to. Therefore, the polarization tucks the dipole, the non-polar molecule become an inductive, just as the happen in the case of iron pieces is brought closer to an magnet. As a result, the attraction take place between the polar molecule and the non-polar molecule. Third is induced dipole attraction. It is easy to conceive the iron attraction and iron dipole attraction and dipole attraction. However, the next very significant question is what is intermolecular force attract non-polar molecule to each other. The other in the liquid and solid state. The origin of these forces was proposed by the Francis London in the 1930 and however hence they are termed as a London force, and these forces of the through to be arise the motion of the electron, and it is believed that the instantaneous the time of the electron could of the molecule may be destroyed also monetary dipole. It is produced in one part of the molecule and slightly negative than the rest. And the momentary dipole induce and dipole in the neighbor molecule, and they are attracted to each other dipole exactly in the same way as the permanent dipole. The dipole attraction between the induced monetary are called London dipole forces. It may be pointed out that since the older molecule containing the electron, the London force are also exist in a polar molecule, and hence in the cases of non-polar molecule, as in the cases of non-polar molecular substance, the London force are only intermolecular force that exists. Magnitude of the London forces and the London force are weakest intermolecular force, and their magnitude depend upon the following two factors. First is complexity of molecule. Larger or more complex are the molecule, greater is the magnitude of London force. This is obviously due to the fact that the larger electron cloud are easily destroyed or polarized. Since the larger molecular size amount to the larger molecular mass, and it obtained suggests that magnitude of the London force increase with increasing the molecular mass. Second is geometry of the molecule. The shape of the molecule has a significant effect on the magnitude of the London force. For example, in pentane, neopentane has the same molecular formula, but the boiling point of n-pentane is 27 degrees Celsius higher than neopentane. The difference can be attributed to the different shape of the molecule. N-pentane has been zigzag chain, whereas neopentane is spherical. The overall attraction between the molecule is greater in the case of an pentane because of their more site of attraction, and the molecule are able to come in contact with either the length of the molecule, and quite the London force is referred to the van der Waals force, and however incorrect of the called London force among the as a van der Waals force. In fact, the van der Waals force is generally termed which impels all type of intermolecular forces. It is interesting to mention here that based on the nature of intermolecular forces, the liquid states are classified into the flowing type: ionic liquid, as such as molten salt, metallic liquid containing of the ion, and the mobile electron. Liquids as a water in the case of molecule are held together mainly by the hydrogen. The molecule liquid in which the molecule are held together by a van der Waals force, which include the interaction among the permanent dipole and induced dipole. Mathematically treatment of the intermolecular forces. Let us consider the interaction between a pair of molecules where the molecules come closer together and their forces of attraction and the force of repulsion between them. Experimentally and theoretically studied both that the attraction force between a pair of molecules were inversely as the seventh power of the intermolecular distance between them. The negative sign has been used. Force is a vector quantity, and if we take the center of one of the molecule as the original with r is equal to 0, the force of attraction is in the direction opposite to the vector for the r is equal to 0 to the second molecules. The force of a force are the considerable magnitude, and the intermolecular force distance are order and little more than the molecular distance. At a very short distance of approach, the repulsion force become applicable between the molecules, but there are generally of the small order in solid because the intermolecular distance are somewhat greater, and it found that these repulsive force are inversely as of 13th power of the intermolecular distance. Net intermolecular force between the pair of the molecule is the sum of the attractive and repulsive forces. Instead of the forces, it is generally more convenient to study their corresponding intermolecular potential, and the potential energy is the amount of work done by bringing one molecule from the infinity to the distance or from the another molecule. A plot of the potential energy due to the attractive force, repulsive force, and the net force, vice versa, of the intermolecular distance at a given in the figure 2.6. For the equation, general written in the form. The potential as given by the above equation is called Lorentz-Jones potential after the name of English physicist who named these studies. Structure of liquid. To study the structure of the liquid means to find how the constituent particles are arranged within the liquid, and the flowing difference study help us to know about the structure of liquid. The volume change on the fusion and evaporation. We can pure solid melt and the increase in the volume only by 1%, which is smaller than that of the increase in the volume which take place when the liquid changes into the vapor of the boiling point. Note that the solid constituent particles are arranged in a perfect order, and when the smaller increase on the volume on melting show a great disorder has been introduced, but the larger change in the volume from the liquid to the vapor state relieves that the disorder from the liquid to gaseous state is very large, and hence we consider that the constituent particles of the liquid are not as ordered as that of the solid, but at the same time they are not as disordered as that in the gas. Enthalpy of fusion and vaporization. The amount of heat required to melt the molecule 1 mole of the pure solid at the melting point is found to be much smaller than that of the amount required to convert 1 mole of the liquid obtained by the vapor at a boiling point. For example, delta H for the ice is 6.1 kilojoule per mole, whereas the delta H for the water is 40.7 kilojoule per mole. Greater amount has been of the heat is absorbed, and greatly disorder introduced. Thus, when we melt a solid, some disorder is introduced in the liquid obtained, but this disorder is much smaller than that of the disorder introduced, and we can change the amount of liquid to the vapor at a boiling point. And this again shows that the constituent particles of the liquid are not as ordered as that in the solid, but at the same time they are also not disordered as that in the gas. X-ray diffraction studies. X-ray diffraction study of the crystalline solid showed that the constituent particle with the solid crystal are arranged in a perfect order, and this is the order extend up to the edge of the crystal, and this is a called long range order. Electron diffraction study of the gases showed that the gas molecule have no order at all, and there is a total cosmetic distribution of the molecule. This structure of the liquid is studied with the help of X-ray and neutron diffraction method, so that they can enter with the entire of the liquid rather than the being reflected on the from the surface. If the like gases, the molecule in a liquid has been absolutely no order arrangement, there would has been like gases, and the molecule in the liquid has an absolute no order arrangement, and there are no has been continuous saturation of X-ray with the maximum and minimum. However, it is not in the cases, and for example, the X-ray diffraction pattern of liquid mercury is shown in the figure 2.7. In the diffraction pattern showed that there is one or two diffraction maximum at a small angle, but as we move outward from the one center chosen atom, the maxima are damped out, and this show that a liquid short range order and still exists, but there is no longer range order. It is constantly to study the location of the particle in a liquid in terms of radical distribution function, which give the probability of finding a particle in range of distance at a distance r from the another. They are easily calculated from the X-ray diffraction pattern, and in the case of only the distance of the neighboring molecule is not angle from the center chosen as are situated studies, and these are distribution curve calculated from the scattering curve in the shown in the figure 2.7. The theory of the model of the liquid. The and the solid are the two extreme state of matter. In the former, there is total choice of molecule, while in the latter there is a perfect order arrangement of particle which keep on vibration about this means position. In the both cases, a mathematical treatment become easier and well advanced theory has been put forward to calculate their property, energy, heat, and enthalpy. However, in the case of liquids, the situation is not well defined and cohesive forces are sufficiently stronger as they are and can be exist in constable state but not stronger enough to hold the particle in a fixed position so that they do have a transitional energy and hence the theory are difficult to handle the mathematically and two common theory about the liquid are brief described. First is vacancy or hold theory. This theory put forward the Arens and Ree in 1933. This theory is based on the fact that the liquid state are generally less damaged than the corresponding solid state. This is implies that the intermolecular space in the liquid is more than that of solid, and Arens and Ree put forward the important view that the liquid intermolecular space will be not random but the compared to of the whole and vacancy of the size of the molecule diameter. Now, thus a liquid can be considered to be consists of the liquid and the holes randomly distributed between them. Due to the presence of the hole, the neighboring molecule can be easily jump into them and Tux showed the gas-like behavior and these molecules which do not have the hole in the neighboring cannot be jump and his showed a solid-like behavior. Using the appropriate mathematical treatment and the mole diffraction of the gas and solid molecule can be calculated from Tux. The value and the thermodynamical property of the liquid can be calculated and the result Tux obtained from the argon by the Arians and Ree will be found to be a closely argument with the experimental value free volume theory. According to this theory, we believe that the molecule in the liquid is surrounded by 10 to 20 neighboring molecule and only was small distance from the molecule Tux. And these surrounding molecule tucks are called form a case or cell around the center molecule as shown in figure 2.7, 2.9 and the tucks the center molecule has been moved only in a small distance to collide with any neighboring molecule unless in a gas where the molecule has to travel a long distance before colliding with the another molecule. Thus the center of the case molecule can be moved within the space shown by the shaded area and the volume tux available to the molecule within its center can be moved free volume and assuming the potential field within the case of the cell is spherical symmetry free volume and can be calculated and this can be related to the various thermodynamic property of the liquid structure and difference between the solid liquid gas. The main point difference between a solid liquid gas can be summarized in table 2.1. Physical property of the liquid, a general introduction. We have been already studied about the gas in chapter first. The liquid difference from the gas is a one important except in the state of aggregation of the molecule. In liquid state, the intermolecular distance are not as larger as in the case of gases. As a result, the intermolecular force of attraction in the case of liquid are much larger as compared that of the gases, and this constantly all through the like gases. The liquid has no defined shape but have a unlikely gases and they have defined volume become of the different between the gases and the liquid are noted about the liquid do not obey the general law or as they are done in by the gases and however the liquid possesses a certain physical property which are characteristic of each liquid. The property help us to decide the chemical constituent of the each liquid and some of the common physical property are called vapor pressure, surface tension, viscosity, reflective index, optical activity, dipole moment. Now we can shall take up the discussion of the first four property one by one. The first is vapor pressure definition. Suppose the liquid is placed in an elevated vessel containing a manometer as shown in figure 2.10. According to the kinematic theory of liquid, the molecule of the liquid are constantly moving in a different direction with the different speed and thus these molecules are moving with the different speed and they are possess the different kinetic energy at a particular temperature and the energy of some of the molecule may be higher than that of the leaving the liquid and come in the space above the liquid and this process is called evaporation. As the time the passes, more and more molecule of the liquid leave the liquid, come in the space above the liquid, and this molecule takes present above the liquid are called vapor, and the molecule of this vapor pressure phase are called conversely moving and into them and strict the surface of the liquid, and may be correspondingly repatriated by the liquid, and this process is called condensation. If the liquid is added into the evaporative vessel, the then the initially there is no molecule of the vapor, and the rate of condensation is however, if the temperature is kept constant, the evaporation continue at a constant rate as shown in figure 2.11 by a straight line plot. Now, with the passes of time, as the number of molecules in the vapor phase become more and more, the rate of condensation also increase. Ultimately, as a stage is reached when the rate of condensation become equal to the rate of evaporation, as many of the molecule re-enter into the liquid as leaves as the liquid in the same time. This state is called state of equilibrium, and the pressure exists by the vapor at this stage on is called vapor pressure, or sometimes called the saturated vapor pressure, as the vapor phase is saturated with the vapor at this stage. Hence, the vapor pressure of a liquid at any temperature may be defined as the pressure exists by the vapor present above the liquid in the equilibrium within the liquid at that temperature. Some important result. Some important results related to the process of evaporation are given below. First is cooling caused by the evaporation. When a liquid evaporates, then the energetic molecule leave in the liquid as a result, and the average kinetic energy of the remaining liquid decrease, and hence the temperature fall. Second factor affecting the vapor pressure. Two important factors on which the vapor pressure of the liquid depend. First is nature of the liquid. If the molecular forces of attraction in a liquid is weak, the molecule can be easily leave the liquid and come into the vapor phase, and hence the vapor present is higher. For example, the vapor phase of the ether is acetone benzene is higher than that of the water at the same temperature. Second is effect of temperature. As the temperature of a liquid is increased, the number of molecules with the higher kinetic energy increase, and the hence the vapor pressure of the liquid increase. This is evident that each of the curve in 2.12. The effect of temperature on the vapor pressure can be studied quantitatively with the help of Kelvin equation. For the evaporation of vapor pressure of a liquid, the equation is written in the form of, as the V1 is very small as compared to the Vs, and neglect the VL as comparison to V, and equation take from the dp by dt is equal to delta H by dV. Further assuming the pressure, we can like an ideal gas where the PV is equal to RT and V is equal to RT by P, and substituting the value of equation second, we get that 1 by P dP by dt is equal to delta H by RT square. This equation is called Calypso-Calipson equation, and this is commonly expressed in another word called the investigation format as right below. D ln P is equal to delta H by RT square into dt. If the vapor pressure changes from P1 to P2, where the temperature changes from T1 to T2, then the interaction of the equation 4 become appropriate limited wet get log P2 by P1 is equal to delta H by 2.303 R T2 minus T1 is equal to T into T. We know that HV and vapor pressure P1 at a temperature T, the vapor pressure P2 at temperature 2 may be calculated. Third is boiling point. At the state where the vapor pressure of the liquid increase as compared to increase the temperature at a particular at a vapor pressure of the liquid become equal to the external pressure is called the boiling point of the liquid, where the external pressure is normal atmospheric pressure, and the boiling point is called normal boiling point. For the normal boiling point of water is 100 degrees Celsius, the normal boiling point of liquid is obtained with the pressure temperature curve as represented by the acetic acid in figure 2.12. Observably, if the external pressure is higher, more the heat will be as acquired to make the vapor pressure equal to the external pressure, and hence higher will be the boiling point. Similarly, if the external pressure is decreased, the boiling point is lowered, and this is the reason that a liquid bowl at a lower temperature on the top of the mountain than that of the sea. So, fourth is heat evaporation. When the liquid start boiling, the extra heat is supplied to the liquid. It is used up to increasing the temperature of the liquid, but to overcome the intermolecular force of attraction existing in the liquid and to exchange by the liquid in the vapor, is the temperature remaining constant till the whole of the liquid changes into the vapor. The amount of heat required to change 1 mole of the liquid into the vapor at the boiling point is called heat vaporization of the liquid. Observably, greater the intermolecular force of attraction present in the liquid, greater is the heat of vaporization. For example, heat of vaporization of water is more than that of the ether and acetone and benzene. Relationship between the boiling point and critical temperature. Glaser point out that the flowing general relationship between the normal boiling point and the critical temperature of the liquid. The normal boiling point of the liquid are nearly two-thirds of the critical temperature, where the both are expressed on the absolute scale. Relationship between the boiling point and the heat of vaporization. Toroyan observed that the flowing generalization of the liquid state which are known associated with which do not have a high boiling point is delta H by T is equal to 21, where delta H is calories, TB is a degree absolute, and this is known as Torreton rule and may be stated as follow. The liquid which have known associated and no do not have higher boiling point, the ratio of the heat of vaporization to the boiling point is approximately 21. Measurement of vapor pressure. Various methods are used for the measurement of vapor pressure are generally classified into two categories: static method and dynamic method. This method has been named because it is static method. The liquid followed the established it vapor pressure without being distributing, while the dynamic method the liquid is distributed either by boiling point or by streaming of the insert gas through it. Some of the commonly involved static and dynamic method are believed below. First is static method is a barometric method. In this method, the two barometric tubes are used, and these are filled with the mercury and called the inverted tube, and some throw a mercury. One tube is used for comparison the other, and one of the tube is experimentally liquid is introduced into a few drop at a time. If the evaporated into the space above the mercury, more and more liquid is introduced, it will be no more liquid evaporate and remain as such. The difference of the level of the mercury into two tubes can is then the vapor pressure of the liquid at a temperature, and for finding the vapor pressure at any other temperature, the barometric tube can be sounded by heating the jacket as shown in figure 2.13. Isotanoscopic method. This method was designed by the systematic and Mises. It is convenient and appropriate the method which can be used to measure the virus pressure over a range of temperature, and the appropriate is shown by the figure 2.14. The main part of the appropriating is the isotanoscopy. The athenoscopy, which is comparise of the bubble B and the U2 portion of the C, and bubble B is nearly is half filled with the liquid under the investigation, and the liquid with same liquid is filled to U2 portion is level of 2 to 3 centimeter below the bulb, and the in isotanoscopy is a place in the stereostat A, and whose temperature can be noted from the thermometer T, and the Isoscopic is then converted into the rest of appropriate width, which is compared of the Manzoni tube. A bigger bottle E is shown in the figure 2.14, and E is converted into the atmosphere of the okay, vacuum pump as considered as regulated pressure instead of the appropriation. This method involved a flowing strap. The first is bottle E is connected to the vapor pump of the appropriate elevator till the boils evaporation in the bulb B, and this repels all the air of the exotic PC, and the level of liquid is in the limb of alto stand then in the L1. Dynamic method. The simplest dynamic method is based upon the principle that a liquid boiling at a temperature which the vapor pressure become equal to the external pressure over a liquid. Thus, the fixing the external pressure over the liquid at different value, the boiling point of the liquid is determined at each external pressure. Suppose the boiling point of T to T3 at the external pressure P1, P2, P3 respectively, then observe the pressure P1, P2, P3 will be vaporized corresponding temperature of any particular liquid. A curve of of type shown in the figure 2.12 is obtained from the curve. The vapor pressure at the temperature can be found. Thus, the dynamic method different from the isotonic method in except that where it is isotonic method and the temperature is fixed first and then the vapor pressure is measured in dynamic method and the external pressure is fixed and first and the liquid is heated to the temperature at which it boiled. The gas saturated method. The principle of this method is briefly described below. At known weight by the experimental liquid is taken in a closed vessel. A given volume of the dry air at a known pressure and temperature is then passed through it. As a result of the molecule, there is no further loss on the weight of the liquid, keeping the pressure P constant throughout, and the air gets saturated with the vapor. In the air saturated with the vapor, if the N1 and N2 are the number of moles of the vapor and the air respectively, then the particular pressure of the vapor, which is equal to the vapor pressure of a liquid at a experimental temperature, will be given by. If the W is the loss in the weight of the liquid M and the molecular, then the N is equal to W by M, and further it is supposed to be the ideal gas where N2 is equal to PV by RT. Subsequent, the value of N1 and N2 in the equation first, the vapor pressure of the liquid can be calculated all at the desired temperature. Note, instead of the dry air, any gas like nitrogen which does not react with the liquid can be used. Surface tension definition. The surface tension is a characteristic property of liquid which arises due to the fact that the molecule of a liquid at a surface area is different substituent from than those of the interior of the liquid, and for example a molecule lying inside the liquid is surrounded by the other molecule, so the attraction is equal to in all direction. Hence in net the force of attraction acting on the molecule is zero, and however a molecule lying on the surface is attraction by the molecule lying on the bulk of the liquid, and then the molecule lying above it in the vapor phase. Thus a molecule lying at the surface experience a net inward attraction. As a result of this inward pull of all molecule lying at the surface behave as if it is under the tension, and hence its property of the liquid is called surface tension. Surface tension of a liquid is defined as a process force acting at a right angle to the surface along with a centimeter length of the surface, and thus the unit of surfactant are dime per centimeter. Further, as a result of this unfair pull of the molecule at a surface, the surface of liquids is tend to contract to the smallest possible area for a given volume of a liquid. It is for the reason that the drop of a liquid is spherical because of a given volume, and a spherical has a minimum surface area. To increase the area of surface, some work has been done assigned in the inward pool. For example, consider the soap solution film containing a rectangular frame of ABCD in which the side CD is movable. In order to extend the surface area of the film, the movable wire has pulled from the position CD to the position EF. This work has been done against the force of surface tension. The work in the erg required to be done to increase and extend the surface area by 1 square centimeter is called surface energy, and the surface energy are therefore called its per square centimeter. Surface energy is equal to work per square centimeter is equal to force into length. This unit will be are is the same as those of the surface tension, and thus the surface energy is same as thing as the surface tension. Hence defined the surface energy is sometime taken as a definite of the surface tension. The value of surface tension of the common liquid at the 220 Kelvin in dynamic centimeter are given in table 2.2. Some important result related to the property of surface tension are brief described. First is a spherical shape of the drop. As already explained, surface tension tries to decrease the surface area of a liquid at a minimum. The droplet of a liquid are called spherical because of the given volume, and a sphere has minimum surface area. Rise of a liquid in a capillary tube. Suppose one end of the capillary tube is put into a liquid, then we get a glass. It found that the liquid rises into the capillary tube to a certain height, and this rise observably due to inward pull of the surface tension acting on the surface center, which pull the liquid into the capillary tube as well. Discuss in more detail in the method of measurement of surface tension. This is because of the same reason that the oil rise into the wick of the soil lamp, and the water below the surface on the earth rise to the plants through the root or ink in the polting of the pen. It may be mentioned here that in the case of liquid, there is no wet glass mercury. The level of the inside the capillary below the level outside further, whereas the upper surface of the liquid, that wet glass on the concave, that the mercury is convex. Such a surface is called therefore meniscus. The angle which curved the surface make it with the wall of the tube is called convex angle and is formed by the drawing a tangent at that point. Third is interfacial tension. If the immersible or particular miscible liquid are taken in a vessel, then the surface tension acting along the surface of separation along with the interference is called interfacial tension. Its value is generally intermediate between the surface tension of the liquid, but sometimes it is less than the both. This is due to the fact that at an interface the molecule of the one liquid are attracted by the molecule of another. In fact, the surface tension of a liquid is always interfacial tension, and the two phases involved behind the liquid are called the vapor above it. Fourth is surface active agent. There are the certain substances like the certain soap, sulfonic acid, and the certain organic compound like the ethyl alcohol, acetone. When added to the water, even a small amount is decreased, and the surface tension of the water is considerable extent. Such substance which have lowered the surface tension of water is called surface active agent. It is for this reason that the soap act as the detergent. For example, if the grease is streaking on the surface of a cloth, water does not wet the grease and had not removed the water alone. However, if the soap is added to the water, it lower and interfacial tension become water and grease. As a result, the grease mix into the water and hence is removed from the surface of the cloth. Effect of temperature on the surface tension. The surface tension of a liquid generally decreases with increasing the temperature and becomes zero at a critical temperature. The decrease in the surface tension with increase in temperature is obviously due to the fact that the increase of temperature, the kinetic energy of the molecule increase, and therefore the intermolecular attraction decrease. An important relationship between the temperature and the surface tension is due by the elbows in the flowing. V is equal to md by k T minus C, where m is the molecular mass of liquid, T is the density of the temperature, Tc is the critical temperature of liquid, the temperature at which gamma is equal to 0. Gamma is surface tension at a liquid where temperature is T Celsius. K is a constant. It may be noted that the relationship m by D is the molar volume of the liquid. If the volume is taken in be the sphere, then the m by d is equal to 2 by 3 is the surface of the liquid, where gamma is the surface energy of the liquid. Therefore, gamma into m by d into power 2 by 3 is a molar surface energy of a liquid. Further, the Ramassamy and Seldig found that the y by md by 2 by 3 is 0 at t is equal to Tc, but at T is equal to Tc minus 6 at a temperature where 6 degrees Celsius is less than the critical temperature. The modified equation has written here. According to the equation, gamma is 0 at T is equal to T minus 6, where negative T is equal to Tc. To overcome the difficulty and Katamia suggestion more correct relationship, where D is with the density of the vapor pressure at a temperature in density gamma is equal to 0, where T is equal to Tc. The measurement of surface tension. There are many methods which can be used for determining the surface tension. Out of these, three conventional and most conventionally used methods are briefly described. First is capillary rise method. This is the most accurate method for measurement of the surface tension. The principle of method is following. Suppose one end of the capillary tube is put into the liquid, where is a wet glass, and then the force of surface tension is put in the liquid into the capillary to certain height. This is still the force of surface tension acting upon the balance the high weight of the liquid volume acting downwards. Suppose the height to which the liquid rise in a capillary is equal to h centimeter. Density of the liquid is equal to d gram cube centimeter cube. Inner radius of the capillary is equal to r centimeter. The surface tension of the liquid is gamma dynamic centimeter in contact with the angle theta, and this component of the surface tension acting in a vertical direction, where gamma cos theta. Inner circumference of the capillary is equal to 2 pi r. For the force of the tension acting upon all the among the surface tension is equal to 2 pi r gamma cos theta, where weight of the liquid acting downward is equal to pi r square h dg. G is acceleration due to gravity, and pi r square h is the volume of the liquid column. Hence, the at equilibrium 2 pi r gamma cos theta is equal to pi r square h dc, or y is equal to r g dz by q. For most of the liquid, where we get theta is equal to z, cos theta is equal to 1. Thus, there are the two parameters that need to be measurement: the inner radius of the capillary tube and the height to which the liquid rises. The former is measured with the help of the traveling microscope, whereas the lateral is measured with the help of catometer. The uniformly of the bore of the capillary tube. The test tube by placing a thread mercury 2 to 3 cm in length inside the tube and measuring its length is difficult to point along the tube. Moreover, by making the weight of mercury and knowing the density at a room temperature, the volume of the mercury can be calculated, and known the length of the mercury thread, the radius of a capillary can be calculated. The stagliometer method. This method is carried out into two different ways as follows. First, A is drop weight method. This method is based upon the principle that the weight of a drop falling slowly out of the capillary held vertical is directly proportional to the surface tension, and thus the two liquid drop of the which fall almost at the same rate out of the same capillary. Whereas gamma 1 and m1 are respectively the surface tension and the weight of each drop of the free first liquid, and y2 and y gamma 2 and m2 is corresponding to the value of the second liquid. And knowing the surface tension of one liquid, then the other can be determined. The appropriate use in the stagliometer and is shown in figure 2.21. It resembles a pipette with a bubble in a middle and mark M on the tube above the bubble, and for however the lower point is made up of capillary filtrate. The producer consists of the following step: the glycometer of the first clean with the chromic acid to remove the greased matter sticky on it, and then thoroughly washed with water. It is cleaned vertically in a clamp stand, and rubber tube with the pin clock of the attached to the upper portion. Distillated water is stuck into the apparatus and then the pressure adjusted with the help of pin clock so that the rate of falling drop is about 15 to 20 drop per minute. 10 drops of the water are allowed to fall into a clean waiting bottle which has been already been weighted when empty. The weight of the waiting bottle along with the dropper is taken. The apparatus is now ionized and with the acetone and then followed by the drive. Now the experimental liquid is stuck into the stegometer and the rate of falling or drop adjusts as below and 10 drops of these liquid are taken into the empty weight bottle and the bottle are weighted. The calculation for out of this flowing. Suppose the weight of the bottle is equal to W1 and the weight of the bottle plus 10 drop of the water is equal to W2. If the Y gamma is the surface tension of water, then the surface tension of experimental liquid gamma 1 will be given as gamma 1 by gamma water is equal to W3 minus W1 by W2 minus W1. Knowing the gamma of water is and gamma of liquid can be calculated. Drop number method, as it will be more conveniently to count the number of drop formed from a certain volume of the liquid that is taken by weight of the drop of a liquid. Therefore the above method may be carried out by in alternative manner as follows. Suppose the number of drop from a V1 volume of the liquid is equal to and the weight of the one drop of the liquid is equal to V into D by N, where D is the density of the liquid and thus it formed the same volume of the two liquid. The number of drop formed is R N1 N2 and the density D1 and D2 are their respectively density. Then V gamma 1 is equal to, hence the drop number formed from the above same volume of the two liquid known by the density and known the surface tension of one of them and that of the other can be calculated. In the producer, the apparatus is clean and clean vertically as before. Diluted water is first stuck into the apparatus to mark M and the number of drop falling out of the capillary is noted and therefore the apparatus is raised with the acetone and dried. The experimental liquid is now stuck in up to the mark M and number of drop formed is counted. Result in then calculating using the formula derivative above. The tensiometer or the Thorism balance method. It is conversely method used for the rapid measurement of the surface tension of a liquid. This method was first devised by the Wilhelm and the later developed by the Du Noy. This method is based upon the principle that the force required to make out of the horizontal platinum ring dissipating dust below the surface of a liquid is directly proportional to the surface tension of a liquid, and the platinum ring used in the usually about 4 cm diameter and liquid is usually taken in a water glass. These the force required in measurement of by attaching the platinum ring is to one end of the beam of a sensitive balance and placing the weight on the another side, or by using a special balance called the Thorism balance. In this balance, the platinum ring is attached to one end of the beam and another end to the beam is fixed to a stretch wire which can be given a Thorism by a stable device. The amount of Thorism just sufficient to taken out by a ring can be recorded on the circular scale attached to one end of the wire as shown in figure 2.22. The experiment is first performed with the water and then experiment in the liquid. Suppose the Thorism angle theta 1 and theta 2 and their surface tension is gamma 1 and gamma 2 respectively. Thus known the surface tension of water, that of the experimental liquid can be found. It may be noted that out of three methods discussed above, only one, the capillary rise method, can be used to measure the absolute value of the surface tension. The another two methods required a second liquid for comparison, surface tension and chemical constituent. The McLeod in the 1923 found the flowing relationship between the surface tension and density. Equation first is found to be hold good over the wide range of temperature for a normal liquid and non-associated liquid, such as that 1924 made use of the above equation to relate the surface tension with the chemical constituent of the flowing as follow. multiply both sides of the equation first with the molecular mass m of a liquid, we get the constant p thus obtained is called Parecore. At ordinary temperature, D is very small in comparison to D, and hence there can be neglect in the diameter. In the equation third become m gamma 1 by 4 by D is equal to P. Putting m by d is equal to v, the molar mass of the liquid in equation third, we become that v gamma 1 by 4 is equal to p. Hence, the partition of the liquid is a molar volume of the liquid at the temperature at which the surface tension and of a liquid is united. The application for a part is descending chemical consists of a liquid is based upon the fact that the partition is additive as well as constructive property. Adductive property of a molecule defined as a property the total value of which is the sum of the value of constitutive atom. Thus, each atom has a defined value for approach, and the total approach value of a simple molecule is the sum of approach value of a constituent atom, and the approach value consisted or associated with the atom called the atomic approach. A constituent property of a molecule is defined as a property which depend upon the constituent of molecule and the arrangement of atom with the molecule. In the case of breeze, it can be found that the total approach value of the molecule consists of the same or some multiple bond or closely ring depend upon the not only upon the atomic approach but also upon the multiple bond in the ring. The approach or value associated with the structure of the molecule and the multiple bond. The closed ring is called the structural parachores. The parachore is a reductive property spotted by using two factors. First is isomeric compound having nearly the same approach value. For example, the approach value for OMP enzyme are nearly same as shown in the table below. Second is difference between the approach of successive number of homozoic series is nearly the same in different homozoic series illustrated by the homologous series of the alkane in the following table. Similar study has been made for the other molecule series such as alcohol, ether, aldehyde, ketone. The average approach value for the CH2 group is found to be 39.0. The above table help us to calculate the atomic approach as follow. As approach is a relative property, the parameter is 17. The parameter is constitutive property is put by the following example. For ethylene, the sum of this approach 2Pc plus 4pH is equal to 78. Actually, the absorbed value is 99.5. Observably, the higher the value is due to the presence of double bond, and hence the approach for the double bond is 21.5. The approach for the double bond has been found in a number of the another compound containing this bond. The average value is taken to be 23.2, and in the case of all compound containing the double bond and triple bond are or a close 3-member or 4-member or 5-member ring, observed value the approach is found to be higher than that of the sum of the approach. This show that this constraint structure may be defined to contribute toward the total approach of such molecule. The commonly accepted value for such sum of the atomic structure approach is given in table 2.3. For what has been discussed above, it may be calculated that the total approach of a molecule is the sum of atomic and structure approach. The application for approach is deciding chemical constituent of a liquid may be insulated with the help of the following example. First is structural of the coin. The following two structural formula has been proposed for a coin. The molecular formula of quinine is C6H4O2. The quinine, according to structure first, is equal to 236.1, and for the quinine of second structure is 219.0. Observe that the approach of the quinine is 236.8. This value is closely to related of the structure first, and hence the first is correct structure of the quinine. The structure of benzene. The structure of benzene as proposed by the Kekule is confirmed by the approaching values as follow. The quadrature structure for the benzene is C6H6 calculate the value of benzene for the approach is 207.1 and density of the benzene at 20 degrees Celsius is 0.878 gram by milliliter. Surface tension of the benzene at 20 degrees Celsius is equal to 29.3 Kelvin by centimeter. The molar mass of benzene is 78 and experimental value of the approach is 206.7. This experimental value is closely in argument with the calculated value and hence the QQL structure must be correct. Third, the structure of perihedral. The acetaldehyde form a polymer called the perihedral having the formula of CH3CHO. This possible structure for this compound are calculate the structuring for approach for the structure first is 363.6. The calculating the approach formula for second is 3 under point 1. The experiment value for the approach is found to be 298.7, which is close to the calculator for the structure second, and hence the structure second must be correct. And structure for the perialdehyde, it may be consist to be mentioned that for any liquid using the calculated value of the approach and the experiment value of density, knowing the molecular formula M for a liquid, the value of the surface tension can be calculated using the formula P is equal to M by gamma 1 by 40. This method of approach studying the chemical constituent out of these nowadays a better physical method are available. Viscosity definition. It is well defined that all the liquids do not follow the same speed like the water and ether for the rapidly, while the other liquid are glycerin and castor oil follow a different quite slower and indicate that every liquid has been instantly resistance to the follow. The internal resistance to the flow posed by a liquid is called viscosity. The liquid which follow slowly observably have a high internal resistance and therefore are said to be more vigorous and are said to be have high viscosity. On the other hand, the liquid have the flow the rapidly were low internal resistance and hence are said to be less vigorous and are said to be low viscosity. To understand the nature of the internal resistance of the friction existing with a liquid, consider the liquid flowing through a narrow tube. All the part of the liquid do not move through the tube and the same viscosity. Imagine the liquid to be made up of the large number of the thin cylindrical coaxial layer, and this the layer which is contact with the wall of all the tube is almost stationary. As we move from the wall toward the center of the tube, the viscosity of the cylindrical layer keep on increasing until its maximum at the center. Conversely, we can say that we can move from the center toward the wall and the viscosity of the layer keep on decreasing, and in another word, every layer offers some resistance and fraction of the layer immediately below it. Thus, the force of attraction which one layer of a liquid observed on the another layer of a liquid moving with the different viscous velocity is called viscosity. It may be defined as that the force of friction between the two cylindrical layers, each of area A has square kilometer separated by a distance x centimeter, having a velocity difference of v centimeter square, is given by the f is equal directly for f is equal to n a v by x, where n is the constant known as coefficient of viscosity. Here the coefficient of viscosity may be defined as the force of friction required to maintain a liquid viscous velocity difference of 1 centimeter per second below two parallel layers 1 centimeter apart and having an area of 1 square centimeter. Some important results. Some of the important results related with the property of viscosity as given below. First is fluidity. Reciprocal of coefficient of viscosity is called fluidity. It is usually represented by phi. Hence, the fluidity in fact measurement in the case of which which a liquid can be flow. The flow through a capillary, it is given by the postulate that the flow of liquid through a capillary tube is given by the flowing experiment, where V is the volume of the liquid that flow in a T under a constant pressure P, and the capillary tube of length L and radius R, and is the coefficient of viscosity. Unit of viscosity and fluidity. As already described, F is equal to N by A, V equal to X. Thus, the unit of viscosity is dynamic second cubic square. This quantity is by the called the Poish, derived from the name of the Poichmer work and Poichule in the field of viscosity. The Poichir Poiser being to be the big quantity, therefore sometimes smaller the unit will are involved, such as centopoic or the millopoic effect on the viscosity. With increase the temperature, the kinetic energy of the molecule of a liquid increase, and hence the liquid start flowing faster. In another word, the viscosity of a molecule of the liquid increase, and hence the liquid start fast flowing. In another word, the viscosity of liquid decrease with increase in temperature, and it has been found that decrease is about 2% of the degree rise of temperature. Number of equation has been proposed connecting the viscosity and temperature, but the best of these is one of the arsenic for the pure liquid, and the equation is where A and E are the constant for the liquid and T is absolute temperature. E is called the an activation energy of a viscous flow. The above equation may be written as log N is equal to log A plus E by RT. Measurement of viscosity. Absolute value for the coefficient of viscosity can be determined by measuring the various parameters involving the Poiseuille formula. However, for the most of the purpose, it is sufficient to find out the relative viscosity with respect to water as reference, and this elimination the necessary for measurement of the number of parameters of above formula are explained below. The for a liquid, the under it hydrolytic pressure, where H is equal to height of the liquid, there is the density of the liquid, G is the acceleration due to gravity, and thus the above formula may be written as where for the equal volume of the two liquid, the flowing for the same height through the same capillary and that of length L and radius are same, and if the N1 and N2 are the coefficient of viscosity of the different liquid, D2 and D1 and D2 are of density, and T1 and T2 are with respect to time of the flow, then thus the measurement of the time of the flow of the liquid, known the density and known the coefficient of viscosity of one of the liquid, that of the another can be calculated. The apparatus used for the measurement of relative viscosity based upon the formula is called viscometer. Simplest is one of the Osto world is called the Ost world viscosity. It is shown in diagrammatically in the figure 2.25. It is consists of externally of bulk B to be a shield a tube above a capillary, and below tucks a mark M on the tube, and the mark M on the capillary as shown, and this lower end of the capillary is sealed to a bigger C, and the wilder tube DE is completely apparatus is U shape as shown in the figure. The producer constraint are the step. The first is the apparatus is filled wash with the chlorine and thoroughly with the water, and it then clamp vertical, and a rubber tube is attached to the end A. The definition volume of is introduced to the bulb seat through the end E, and the quantity of water added should be more than that of the required to fill the bulb B. Third, through the rubber tube attached to the A, the diluted water is struck up, and the bulb B so that the level of water is little above the mark M, and the water is then okay, allowed to backflow so as the time taken by the water to flow from the mark M to M dash is noted. Fourth is the apparatus is then dried. The experiment is respective as the above taken the same volume of experimental liquid. This the result in calculating using the formula derivative above. The value of the coefficient of viscosity at 20 degrees Celsius for the same common liquid are called recording table 4.4 below. Viscosity and chemical constituents. No significant relationship between viscosity and chemical constituent has been put forth, and so far, however, no so general result has been observed were we summarized below. In a homologous series, a viscosity increase, so we can go up in the series and increase per CH2 and the same group is almost constant. In the compound involving the chain isomerism, the N isomer has been generally greater viscosity than that of the branch chain isomer. In compound involving the geometrical isomerism, trans isomerism has a higher value of viscosity than the corresponding cis isomer. To predicate whether a liquid associated or not, the Duchamp proposed a rule called Duchamp's rule. According to this rule, for a normal liquid, the non-associated liquid. For association liquid, the value is much higher than of it than 80, and the value of few associated and non-associated liquid is taken to in the table 2.5 below. Fifth is Record. Just as a Pecor is a adductive and conjunctive property related to the surface tension, effort were made to drive the simple quantity related to viscosity, then which will be additive and constitutive in nature. One of such quantity form is named as Record, which is related to the viscosity by the given expression, where M and D and N are the molecular mass and density and coefficient viscosity of a liquid, where N is equal to 1 and R is equal to M by D is equal to V. Hence, the viscosity record may be defined as a molar volume of a liquid at a temperature at which the coefficient of viscosity is unit. However, the use of the record is additive and constitutive property was found to be very limited. Hence, the term could be not again any significance. It may be mentioned here that the most important application of the measurement of viscosity is determined of the molecular mass of polymer by finding the viscosity of their solution in appropriate solvent. The principle of such determination is follow. The viscosity of a solution is n at the concentration C, and the viscosity of pure solvent n node. Then the specific velocity of a solution is defined in the relation n minus n node by the n node is equal to nsp. The plot of NSP by C, where C is found to be the linear and the value of NSP is obtained by the extrapolation. The plot to be zero concentration give that called the vinegaric viscosity is found to be related to with the average molecular mass of a polymer M by the equation, where K and A are constant for the given type of polymer and a solvent. The value of these constituents are found to be first performed the experiment with the two samples of polymer of the same series whose molecular mass has been already be found by the other method. Reflective index definition: when a ray of light travels from one medium to another medium, it go or change direction as shown in figure 2.24. The phenomenon is called refraction. It may be it if the ray of the light travel from a less dense medium to the more dense medium, the ray is bent toward the normal. It observed by the Snells that if the ray of light travel from air or vacuum to the more dense medium, then the ratio of the sine of angle of incident to the sine of angle of refraction is constant. Depend upon the nature of medium, and the constant is called the reflective index of the medium. It is usually represented by mu, and this is called Snell's law. The value of refractive index is also found to determine the wavelength of the light use and the temperature. Tux they are usually specified as an subprecative and super subprecative respectively. Tux the indicator of a refractive index has taken at 20 degree and the light corresponding to the yellow D line of the sodium spectrum obtained from the sodium vapor lamp. Alternative, the refractive index a medium is also defined as a ratio of velocity of light and volume to the n velocity of light in medium. In the Snell's law defined above, the first medium chosen is air and or vacuum. Internally, if the ray of light travel from less dense medium to the more dense medium, then it will be observed that sin I by sin R is equal to capital N by small n is the refractive index in less dense medium, n is a more in the more dense medium. Measurement of refractive index. The measurement of refractive index is based upon the phenomena of total internal reflection and the critical angle. Let us therefore first try to understand three phenomena clearly. Suppose a small source of light is placed in a line with the interface of the medium R1 and R2 are indicated ray as angle of incidence increases and the angle of refraction also increasing. The ray R3 is almost gone along the interface. The angle of incidence for this ray is therefore nearly 90 degree and the angle called the grazing angle of incidence. Thus for the R1 minus R3 for which the angle of incidence is less than 90 degree and refractive ray is R1 minus R3. The ray like the R4, R5, R6, etc., having the angle of incidence greater than the 90 and undergo the reflection with the medium second. The corresponding reflective ray are called R4, R5, R6, and this is called total internal reflection for the ray. R3 angle for I is equal to 90. The corresponding angle for refractive index is maximum angle of refraction and is called the critical angle, usually represent E. For the figure 2.28 it may be seen that a bright band of light is observed corresponding to the refractive ray R1 minus R2 and the darkness on the inside. Either side, the edge of this bright band corresponding to R3 will be give the measurement of the critical angle. This edge of bright band can be observed by placing a telescope called the rotation about the point O. The instrument measuring the refractive index is called refractometer, and two common refractometer are Polkfish refractometer and Eaves refractometer. The first refractometer is used for the Parrish measurement, where the second is used for rapid measurement. The second apse is described below. The principle of apse is represented in the figure 29.2a is whereas the design of the instrument as shown in the figure is constituted the external of two right angle of P and Q with the hypotenuse face together. It may be claimed together with the claim X is a metal box hung to the Y and as shown in figure 2.29 the box is attached to the arm R with the help of which the prism system can be rotation and the value of refraction index can be read directly on the circular scale fixed at the top of the arm R and the hypotenuse face of the lower sphere prism is ground whereas that of upper prism is polished. A drop of the liquid is placed on the hypotenuse face of the prism P which separate between the two faces. When the two prisms are fixed, the light are stable source in them and reflect by the medium M on the liquid as the layer and shown in figure. On striking the ground, the surface of the prism P, the light gets diffused at all the direction and thus the ray are indicated on a polished face of the prism Q at the angle less than 90 degree and at the angle greater than 90 degree. A picture of this concept is shown in figure 2.29. See the ray incident at an angle greater than 90 under the total internal refraction with the prism Q do not come out of the prism Q and the ray at angle less than 90-degree refraction and come out of the prism Q in the form of the brightness band of the light is of the egg of the light and bond corresponding to the grass intense to a telescope is fixed at the prism system and the boxing inside the prism system is rotated with rotate till the edge of the brightness bond conceived with the crosswire of the telescope. This setting is corresponding to the refractive ray and refractive at a critical angle. However, instead of the measurement of the angle, the circular scale is gradually directly to for the reading of the refractive index. Refractive index and chemical constraint. Attempt has been made to relate the chemical constraint of substance with the reflective index. The number of now term has been put forward as explained below. First is specific refractivity. If it has been found that the flowing substance leaving in refractive index and density at a same temperature, the expression the is constant for a particular substance independent of temperature. The quantity R is also called a specific refractive index and the specific refraction of the substance. The term was put forward by the Lewis-Chance and the Lewis-Geertz in the 1880. Molar refractive index. Multiplying the specific refractivity to the molar mass m of a substance, we get what is the known as refractive index. So, molar refractivation. The formula is applicable to the gas, liquid as well as to solid. To determine the molar refractivity of a solid, it is dissolved in a stable solvent and the complex and the refractive index and density of D of a solution are measured. The molar refractivity of a solution can be determined the formula where x1 and x2 are the molecular refractivity of a solution and is the sum of the contribution of made by the solute and the solvent. Hence, the R1 is the molar soluble reflectivity of a solvent and R2 is the solid and thus the known as R1, R2, R3 and can be calculated. Like the approach, the molar refractivity has been found to be additive as well as conductivity. The additivity nature is supported by the fact that first is difference in the molar refractive of the successive member of homologous series is nearly constant, and second, the isomeric compound with the similar structure are found to be nearly same value of the molar refractivity. Similarly, the constituent nature is supported by the fact that in the case of compound containing double bond, triple bond and closely ring, the observed value for the polar refractivity is higher than the value conscious of simple addition, the atomic refractivity. The value of atomic refractivity has been calculated in a minor simple to done for the approach table are available for conducting these values. However, while calculating the molar reflectivity, the following 2 points has been kept in mind. First is atomic refractability of oxygen atom is different in alcohol, ether and ketone, where a compound containing more than one double bond, triple bond, or molar refractability depend not only the number of double and triple bond but also on their reflective position in the molecule. When the double bond or triple bond are present in a conjugate position, the molar refractivity is higher than the calculated value known as optical acceleration. The application for the molar refractivity is deciding chemical constituent of a substance may be isolated with the help of example first in given below. However, even this method has been found only the limited application in deciding the chemical constituent. Liquid crystals. A large number of organic compounds with the long chain molecules like the acetic acid, clistoacetic acid, clistoethyl benzoate, Ammonia exolate are known to help which on heating melt sharply to give a milky liquid of which on further heating become clear against at a different defined temperature. The former temperature is called the transmission point whereas the latter is called the melting point. For example, the p-hexoacinol transfer point is 389 K and melting point is 40 K. On cooling the clear liquid, the receipt change which take place exclusively at the temperature. The thermic liquid thugs obtained are found to be anisotropic, a property observed by the crystalline substance. According to this property, like the refractive index, the refractive conductivity are found to be different in different direction. Hence, these thermally liquid are called liquid crystalline. However, it is found that the molecule of liquid crystal do not have the arrangement like that of the crystal lattice. Moreover, exception for a few properties, they have believed that behave like a true liquid, and they are moreover except a few properties, they behave like a true liquid, and they possess the surface tension and have the property to flow. Hence, in the place of liquid crystal, the certain other possess surface tension and the property to flow. However, the place of the liquid crystal, certain other name has been proposed such as anisotropic liquid or peristopic. The best name of the substance is the state is mesomeric state. However, in the spite of the old days, the original name liquid crystal is still frequently used. The type of liquid crystal on the basis of the molecular arrangement, the liquid crystal are classified into the following three types. First is neomatic liquid crystal. This crystal, the molecule are lined up in such a way that their long axes are parallel to each other, but the molecules are not arranged in a layer. The parallel molecule can be slide past each other, and the name is pneumatic comes from the Greek word means thread, as appeared thread-like, which is seen in a microscope, and the crystal is translucent, less tubular, and quite mobile, and can flow further to spread the light strongly. Some example of this compound given the new liquid are shown in figure in the table 2.7 below. Second is symmetric liquid crystal. In this crystal, the molecule do not have their long axes parallel to each other but also arranged in a layer as shown figure 2.30. These parallel molecules in a plane can slip past each other, and the name symmetric has been derived from the Greek word soap, as there are these crystals of this soap in touch, and the structure these crystals are more tubular and viscous than the pneumatic liquid crystal. Frequently, asthmatic substance is transferred into pneumatic substance during the course of heating of to the liquid temperature. Some examples of corresponding weld split of the liquid state are given in table 2.8. Third is chlorhistoric liquid crystal. In this crystal, the arrangement of molecule is similar that of the pneumatic liquid crystal. However, in this case, the crystal originates of the axis shift in a regular way is going from one layer to the next layer, thereby the given hexagonal structure in as shown in figure 2.30. Because the structure, the crystal has been remarkable optical property of refraction of different color under the different condition at a different temperature based upon the property using the crystallic liquid crystal are available with the which color range with the person mood and with one skin temperature. The name of the crystal has been given to these crystals because these substances are all derivative of the cholesterol. Use of liquid crystal. First, liquid crystal are used in the wristwatch and other electronic instrument in which the digital visual of the black number take place against its silver background. Second is thin film of the clearosteric liquid crystal are used to map the skin temperature as the aid to the diagnosis of the diseased tissue and the ring to study the person mood as already explained. Difference between the liquid crystal, solid, and the liquid. The main difference between the solid liquid and the liquid crystal is the long range order of the molecule. In a crystal solid, there is a complete long range, whereas in a liquid there is almost complete long range disorder and almost no longer range order in at all. The liquid crystal represent a microscopic state. An intermediate can be between a solid and a liquid, and there is no have a perfectly ordered arrangement of this molecule like that of a solid. Still, they have no more order than a liquid is observed from the X-ray diffraction study. Further, as already mentioned, some crystallization solid on heating from the somatic liquid crystal, whereas some other give the neomatic liquid. Both of these type of liquid crystal has been less odor and then of the solid but greater than the liquid, and some of the somatic liquid crystal have more and odor than the neomatic liquid crystal, and there is some of the crystalline solid which have no heating first from the geometric type of liquid crystal which have known further heating with the pneumatic type of liquid crystal which have on further heating melt to a form of a clear liquid, and a common example of this is called the chloro cholesterol mystery labeled state. The change in this following way. Thus, there is a two transform temperature and one melting point. To represent the structure difference between a solid and stomatic liquid, the pneumatic liquid crystal, a clear liquid diagrammatical. Let us take the example of crystalline solid of the type of crystal mystery. In this crystalline mystery, there is a complete long range order in three-dimensional. All the molecule has the same origin and have a regular arrangement in the different plane as shown in the figure A. On heating with the turbid liquid called the stomatic liquid crystal, in this state all the molecules have the same origin and they are in the equiplace plane, but the arrangement between the plane is irregular as shown in figure 2.31. The substance have no longer crystalline in is more ordered than the liquid. On further heating, the turbidity decreases and at a particular temperature and a new state is obtained called pneumatic state, in which molecules still have a same origin but have a new state obtained called a pneumatic state, in which they still have the same origin but they have no longer escaped plane as shown in figure 2.31c, and this order is introduced but the some order is maintained because of all the molecules still have the same origin, and on further heating even this order is lost and the substance in the liquid state as shown in figure 2.31. Thermatography. It is a technology recording the temperature variation explicitly of the skin on a graph. The recording thus obtained is called thermography. It is based upon the fact that because of the empirical structure of the chlorothistic liquid, they have been remarkable optical property of refraction light of different color under the different temperature. This is because the helical structure has a characteristic pitch length, and the pitch length are in the range of wavelength of visible light, and the pitch length change on changing the temperature, but the chemical structure of the helix remain unaffected. The property of different liquid crystal are described in terms of event temperature, clearing point temperature. The lowest temperature has a liquid crystal secreted the visible light is called the event temperature. At the temperature below this, the temperature, the liquid crystal may be the solid state and will be appear transparent. The temperature above which it become pure and liquid is called the clearing point temperature. Depend upon the requirement, the stable liquid crystal can be selected which reflect the light of different color is described below range. The most of the application of the thermatography is been in the medical field in the recent years. Especially it is detection and technology of tumor and breast cancer beside the orthopedic disorders such as arthritis, back pain, etc. The principle is that the heating change produced is affected the skin in different form of healthy skin. Earlier, the physician used to paint the liquid crystal on the portion of the body to have examined, but the method was too tough and roughly. And now the method is simple to liquefy the crystal as perceived against the heater and as well as a part to be examined, and the color of the photography are taken of the resulting pattern of the color and then compared. In fact, the principle has moved. The thermography has been used since very early time, and the ancient Greek physician employed a primitive method of terminology. They are used to apply a thin and surgery on the area of their patient body, and the pattern of drying and they determine the abnormal distribution of body heat, and this technology is called medical terminology. Liquid crystal display and the seven segment cell on the most important application of the liquid crystal has been in the electrical industry. It has been used thin light weight display device such as this digital watch, pocket calculator and similar instrument. As this is done by which help the liquid crystal is called the liquid crystal display. This principle as follow: the thin film of the liquid crystal, not more than the thousandth of a thick ink, is placed between the two sheets of the glass, one of which is coated by the another in a thin layer of the electrical conductivity metal, such as the thin oxide. There is no current is passed through the conductivity cord, and the molecules are uniformly oriented, and the light was passed through the cell. When the current is applicable, the molecule aligned change because of the liquid crystal molecule are polar, and the cell appear aqueous or black, and the number or the letter is displayed in the black assigned in the silver background. A liquid crystal display a very small current is assumed very little power. Electronic watch and calculator run for the year with the small battery. Mostly the display of LCD watch and calculator are composed of the seven segment, and the section can be display one number, which the combination of this section display the number, and similarly for the alphametric display there is 14 segment. A segment means an active area in which display or image area. The complete display and plane is compared of two polaric, that the instrument light is perpendicular direction is mirrorized, and the surface area and a layer of liquid crystalline matter become between two glasses plate are shown in figure 2.33a, and this in the absence of this applied voltage, the liquid crystal molecule in all the segment are possibly assigned, and therefore the entire plane appears silver. Become light passes through the both polarized reflective black of the mirrored surface, and then again pours through the both polarizer. When the voltage is applied to the sign display or pressure assigned of the liquid crystal, molecule is lost, and this results in polarization. Light from the first polarizer not from being rotated at 90 degrees align with the second polarizer, and the second polarizer block the passage of light and cause the segment of a planar to appear black.